My name is Kamil. I am iOS developer in Allegro, and today I would like to show you some hacks. Somebody from the audience already told me that this is not a real hacks, but come on. Let's assume I used some numeric system with base of 36, and everything's working now. So, in the first part of my presentation, I will be talking about Mach-O format. Mach-O is a container for executables and libraries on Apple platforms. In the second part of my presentation, I will talk about obfuscation. It may seem that those two subjects have nothing in common, but I will show you later how they correlate. Okay, Mach-O is pronounced the same as a main power source in Final Fantasy VII, but they have nothing in common. Mach-O has a lot in common with Matrix the movie. This may seem like totally random byte stream, but if Neo was here, he would for sure see people, cars, buildings. And I have good news for you. I will now give you an ultra-fast crash course of understanding the Matrix code. And the Apple platform will be our Matrix. So let's freeze the image and zoom in. Any binary data format starts with some arbitrary value, so-called magic number. I think some of you can already see that first 4 bytes of this stream are very similar to the title of this presentation. Similar, but written in reverse order. Why in reverse order? Because of the little endian format. In little endian, when we write bytes as a number, the least significant byte is written as a first one. So the magic number in the stream is really FEED, F-A-C-F. So how Neo can know what does this number even mean? What is the byte stream? Well, the value is defined and described in macOS system headers. There is one system header that describes the whole Mach-O format. And inside this system header, we can see definitions and descriptions of 2 magic numbers. The first one is equal to the title of this presentation. This magic number indicates 32-bit Mach-O file. The second one is very similar. It indicates 64-bit Mach-O file, and as you can see, it is equal to the magic number here in this stream. And what now? Neo knows that this stream is a Mach-O file, but what now? Well, Neo needs to read some description from the system header describing Mach-O file, and he learns that each Mach-O starts with so-called Mach-O header. And this header can be described with this struct. So it begins with 4 bytes of magic number, as we already seen. Then comes the CPU type, CPU subtype, file type. File type designates if this is a library or executable. Then number of so-called load commands. I will talk about those load commands later. Then some size of comments, some flags, and some reserved area, reserved for future use. Let's color up matching byte areas. And those numbers still looks a little mysterious, but the system header that describes Mach-O format, it defines and describes all these magic numbers. Let's just replace those magic numbers with human readable descriptions. And now we understand that this byte stream describes 64-bit Mach-O file compiled for all subtypes of 64-bit Intel CPUs. This byte stream is an executable, and it contains 20 load commands. Okay, let's now talk about those load commands. Reading the system header reveals that load commands comes just right after the Mach-O header. And the base form of a load command looks like this. It begins with 4 bytes of load command type, and then 4 bytes of command size. Let's color up the matching byte areas. Now you can see just a short snippet of what's coming next. You see the first load command. This load command has type equal to hex 19, and it has size equal to hex 48. And the white area is more detailed content of this load command. So from the beginning to the end of white area, you have 48 bytes in total. Then comes another load command, and another, until you parse 20 load commands. What now? We have load commands, but we don't understand what's inside. Well, Neo has to read more contents of system header, and he sees that there is a couple of load command types. For example, load command segment. Load command segment is used to map some byte area from the file to the operating system memory. Another load command, UID, it does not map any memory, but it is used it holds a unique identifier of a Mach-O file. So when you use Crashlytics and Crashlytics says, hey, there is no decims from that UID, that's the UID in this load command. Next, load command rpath. Rpath is used to hold a path to the directory that contains all frameworks, all dynamic libraries. So, for example, when you're dealing with iOS apps, this rpath contains a path to the frameworks directory. And load command dwld info, very important. I will talk about this load command later. It's heavily used by dynamic loader. So where you start the app, dynamic loader uses that load command to set everything up. And as you can see, parsing manually Mach-O is really hard, and it can be very painful. So let's just skip some of this work. I will just replace all those non-zero bytes using ASCII codes to show you that there is a lot of meaningful data. And here is the job done. You can see Mach-O header on the top and some of load commands. And for example, the first load command here, text, it is used to take first 1000, hex 1000 bytes and put it into the RAM of your machine. Each segment can consist of several sections. In this example, section lowercase text, this is the section that contains all the assembly. So all the code, all the functions, all the methods, they are placed here in that range of bytes. Load command main, it just holds a pointer to a place in the file, and you can see that this pointer lies exactly within this range. So this is a pointer to some function And as you can imagine, this is the pointer to the function main, to the main function of our program. When the program starts up, dynamic loader takes that pointer and he just resets the instruction pointer to that value. Load command load dynamic lib is used to load dependencies. So whatever you're using UIKit or Foundation, this load command will tell dynamic loader to load that into the memory. Okay, we do this I showed it to you so you can feel that how hard it is to parse it manually. But hopefully there is a tool in every macOS that will does it for you. OTool with L parameter will parse the Mach-O header and load commands. And using the verbose mode, you will not see all those magic numbers, you will see the human readable descriptions. Okay, let's go back and take a look at contents of one section. That section is C strings. This is the section that contains all constant strings within your app. So let's jump into this range of bytes. And it is very short in this case because that was only the sample app prepared for this presentation. Let's replace those bytes using ASCII codes. And that is how Neo saw the woman in red. Okay, jumping between byte ranges is very painful. You can do this using OTool with S parameter, and this will print contents of any section in any segment. Let's print contents of Objective-C metname section from iOS system calculator. And as you can imagine, this section contains all method names defined for Objective-C in that image. So let's replace all the bytes using the ASCII codes. And init with frame, set transparent, appearance named. This seems like a selectors list, well-known selectors from iOS, but also some custom selectors. Okay, let's try to display another section from Mach-O file, Objective-C class name section, and replacing all the bytes using ASCII codes. Show us bit field box, calc, button, cell, so the engineers from Apple didn't use any prefixes on Objective-C class names. Okay, those are 0 separated string lists. This is not very sophisticated data structure. Mach-O contains a lot of very complex data structures. For example, there is a section that describes a class hierarchy, or a section that describes each class, its properties, methods. It is very complicated, and we won't talk about them today. But we will talk about another complicated data structure from Mach-O. There is a load command dyld info, which I told you before about. And this load command, it points to a structure called export try. Export try, it looks like a tree, but it's not a tree. In case of a regular tree, when you are looking for some value, each node in a tree contains a full key, so number or string, and try is constructed to allow you very fast search using very long strings. So each node contains just a key fragment, not the whole. Okay, what is export try? Export try is a structure that describes all symbols that you can access from the library. and also the pointers to the assembly, the place in which the function is defined. So in order, imagine some executable that would like to call any Objective-C method. This executable would probably need Objective-C message send function. So during the app startup, dynamic loader would look from the root of this try via underscore Objective-C underscore message send, and he would say, okay, here is the pointer to the function that the executable needs. Okay, so this try contains 4 symbols, and this can be flat printed like this, but the try structure is really fast. Okay, so load command divide the info on one side points to the export try, but there needs to be some import side on the other side. And that is the bindings list. And in bindings list, each binding points to some symbol, referencing it via its name and library. If you would like to read more about the try structure, then you can read it on Wikipedia. And as you can imagine, I only showed you only the very peak of an iceberg about parsing Mach-O files. There is much more information in this topic, but good news is that all the important stuff is located in exactly one file on every MacBook, on every Apple computer. And this is the file. You can think of it as complete documentation about Mach-O structures. It's very detailed, but also very easy to read. It contains a lot of struct definitions, but also a lot of human-readable documentation. If you have any problems with sleeping, you can print it and place next to your pillow. You will sleep for sure. Okay, congratulations. You all have completed an ultra-fast crash course of understanding the matrix code. I am sure that all of you should now see the woman in red here. Does anyone see woman in red? Oh, good one. Okay, this completes the first part of my presentation. Mach-O format is very Apple specific, but if there are any Android developers, then good news. All the stuff described here applies also to other platforms for Android, Windows, Linux. Let's now talk about obfuscation. What is obfuscation? Is an act of making everything looking different, so it would be very hard to statically analyze that thing. And here is an example of obfuscated function. And can anyone tell me what does this function do? No, not Fibonacci. Okay, I only meant to show you that this function is hard to understand. Let's look at an obfuscated version of this function. Can anyone tell now what does this function do?
It's a power function?
Yeah, exactly. So it was much easier than that previous function. And this type of obfuscation is a control flow obfuscation. So it's pretty hard to achieve in case of everyday apps, because I think every one of us is using optimizations during the compiling. So this code and this code could end up as exactly the same assembly. So no obfuscation at the end.
Okay, so it's not a power function, it's a factorial.
Factorial, yeah, yeah. So
Okay, it looked wrong.
yeah.
I'm sorry.
Here you can see another type of obfuscation. It is much easier to achieve in case of apps when you have a lot of business logic, when you are dealing with object-oriented programming. And the control flow is pretty obvious, but all the symbols are unreadable. So this is an example of symbols obfuscation. Without this obfuscation, this function would be pretty easy to find, very easy to modify, and whole app would be very easy to crack. There is another type of obfuscation. It's obfuscation so advanced that it looks like a magic. And this is the obfuscation that was used in Hopper decompiler. If you try to decompile the Hopper, not using Hopper because Hopper can't decompile Hopper because it's protected against such a thing, then if you take another decompiler and decompile the Hopper, and if you look into the text section, a section that contains all methods, all functions, you would see something that doesn't make any sense, some unicorn, I don't know, something like that. And it happens that Hopper contains one additional load command that has 12 megabytes of, you could say, random data, but this data is not random. And what dynamic loader is doing, it takes contents of a faked text section. He takes that 12 megabytes of random data, and he XORs them together, and in the result, he gets the true code, true assembly of the Hopper. So, magic. I encourage you to watch that movie. There is a lot of more freaky things. So, if you would like to take a picture. Okay. I told you about Mach-O files. I told you about obfuscation. Why? Because I wanted to tell you about my idea for the obfuscation. This idea is not to obfuscate the source code, but to obfuscate the compiled Mach-O file. And this URL contains the implementation of my idea. I encourage you to read the Readme. It contains a lot more details that I will be able to tell you tonight. And I encourage you to use it or to contribute. And it is written in Swift. The Objective-C is only in unit tests, so don't worry. How does it work? Well, it changes some of the sections from the Mach-O. I don't know if everybody see the slides because do you see everything or no? Can I move this a little to the? Okay. Okay. So obfuscating symbols from Objective-C class name and Objective-C met name sections, which I showed you before, protects against tools such as class dump and Hopper decompiler. Next, Swift compiler adds some sections that can be that are used as a substitution of reflections of introspection in Swift. And example of those of those sections are these two: Swift typeref and Swift refl str, and they are used by the structure called mirror. You can construct this mirror for any object in your code. Then you can print all the children, superclasses, and you can do introspection. What does Mach-Obfuscator do with those sections? Fills them with zeros. And I read the implementation of the mirror struct on GitHub, and this seems to be pretty safe. And test apps are working after zeroing out those sections. If someone thinks it's not safe or knows any reason why I shouldn't erase those structures, then please let me know. And what's strange, mirror still works after filling those sections with zeros. It just returns less detailed data, so no information about properties names, just the types. Then, load command dyld info, the one that points to export try and to bindings. This is used by dyld. I don't know any tool that uses information from that load command for static analysis, but it can be obfuscated, so why not? And load command symtab. This load command has a pointer to the symbols table. And this symbols table, it is used mainly by LLDB. When you want to put a pointer using the command line, you start to typing the method name and you press tab. Then symbol tab is used for autocompletion. So erasing symtab just makes autocompletion unavailable. Also, the hopper uses the symtab, so after zeroing out, hopper doesn't show any symbols in the binary. And as you already see, Mach-Obfuscator doesn't need any source code. And the same is for UI. So it doesn't operate on XIPs, it decompiles NIPs and obfuscates NIPs. Now, how does this obfuscation proceed? First, Mach-Obfuscator looks for any executables within the app bundle. It looks for all the dependencies of those dependencies, until it finds all possible dependencies that would be loaded during the app startup. Then it marks found images as obfuscable and unobfuscable. Obfuscable because those images are within the app bundle, so we can modify them. And unobfuscable because they are read-only and they are, for example, system libraries. Then Mach-Obfuscator takes all the symbols from those files, from obfuscable and unobfuscable. And now Mach-Obfuscator needs to decide which symbols could be obfuscated. So it just drops everything that ever be read. And we are left with a relatively tiny list. But if you try to read the methods to obfuscate, retrieve orders, clean cart, this seems like a business logic, the things that we want to obfuscate. Let's now do some comparison. I wanted to show you that this obfuscation is different than source code obfuscation. There is no silver bullet, so no of these solutions is better or worse, they are just different. Both has downsides and advantages. And as for the binary obfuscator, it is language agnostic. It obfuscates Swift, obfuscates Objective-C. If Apple decides to release a new programming language next year, binary obfuscator is ready for that. Probably would need some kind of development to erase any additional sections, but it would work. As for the source code obfuscator, you would probably need a new one. Binary obfuscation works for external libraries, so all the CocoaPods and all the libraries provided as a compiled version. So, for example, Google Analytics. And binary obfuscation doesn't affect crash symbolication. Are there any Android developers here? Yeah? Do you know what is crash symbolication?
No.
Okay, so I will tell about this in a short. So when the iOS app crashes, system generates a crash log, but this crash log is not human readable. It does not contain stack trace in a form of a string list. It contains an array of pointers to the functions. And nobody could understand that unless he have a decim, the file that can be used as a dictionary to translate pointers to the strings. So decim is generated during compilation. Obfuscation is done after the compilation. So binary obfuscation doesn't affect symbolication. In case of source code obfuscator, it probably needs some tool to translate the crash logs to the form readable by human. But binary obfuscator also has some downsides. And it will not work any new incompatible sections in Mach-O files. When Apple decides to change Mach-O format to something different, also this obfuscator would be need to rewritten. Also, the source code obfuscator just renames the source code, so the user could feel a little more safe about this. This is no so binary black magic. And interesting fact, funny fact, we had a problem with Allegro iOS app that Apple rejected our binary because it contains hidden or undocumented features, and they wrote that we should remove all code obfuscation. I cannot tell you how this story ends, but you probably can imagine. And what I wanted to tell you, Mach obfuscator contains an algorithm that could protect against detecting the fact of the obfuscation. Mach obfuscator contains a list of 10,000 the most popular English words, and it uses it to generate random symbols. If you look at this looks like a pretty normal method of property list. But if you try to read it, then poem doc doesn't make any sense in case of a banking app, does it? Okay. Conclusion, because every presentation needs one. I think it is worth to learn something about Mach-O. I personally focused on the obfuscation, but I think all of you would have very clever ideas about using the Mach-O, about parsing the Mach-O. As a reminder, here is the system header that you need to put under your pillow. Here is the Mach obfuscator. I encourage you to read the Readme, to contribute, or to just give me a star on GitHub. And here is my Twitter. If you have any questions about this obfuscator, about obfuscation, about the compilation, then you can ask me now, or you can chat me at Twitter. Thank you.
Do you consider this obfuscator production ready?
I never tried to obfuscate a production app, but I'm planning to do this as soon as I support obfuscating core data. And then I have a little app on the App Store. Nobody uses, so I will try to obfuscate and upload it. And hopefully this should work, or not.
Okay, I have also a second question. How does it work in mixed language environment? I assume there is no difference, but something like mixed Objective-C, Swift, Objective-C++, and C++.
Okay, the question is about mixed language environment. So in case of using just the Swift, all the frameworks are still written in Objective-C. So Swift calls the Objective-C. And as for C++, I didn't try to see what happens. Maybe I should write some C++ code and look what happens after the obfuscation. Thanks. Yep.
Or I have a question like, since we all want to obfuscate the code, but as you said, it's like Apple doesn't pass this code for their reviews. So is it even worth it? Try it if they won't pass it.
Okay. From the question is it worth it to obfuscate the app? So it's always worth.
Have it in production and on App Store.
It's always worth to do this because you destroy another vector on attack for your API, for your backend, for example. And was the first part of your question?
Yeah, if you can't get your applications to be on production because App Store won't accept it, so
okay.
You can have it obfuscated, but
that depends. Some people told that they had a problem with the obfuscation. Some other people told that it's absolutely fine. So you never know when the lightning strikes you.
it's just a wild guess.
But I think there is some hope in this obfuscation with random words. But let's imagine something like that. I have a colleague in some bank. I won't say the name of this bank, but they write code in Java in Polish. And so the code, the setters getters looks like get cena, set cena. Cena is price in Polish. And imagine somebody using Chinese or Mandarinian on emoji language to write a code. And what Apple? Do you think that Apple will hire someone knowing that language and checking the selectors, whatever they contain some improper language or something like that? I think they only looked into the obfuscated code, and this code looked like base 46, for example, because that's the most popular way to obfuscate the symbols. And I think they thought, oh, we have obfuscation, but they really didn't check what's inside.
Right, so it's kind of like officially it's against their terms of and conditions.
There is no official information about the obfuscation. Apple has a lot of reviewers. Some of them could feel in duty to protect against any weird stuff, and some of them just don't give a care.
Yeah. I will add one thing about this email we've got. We've got the same.
Oh.
Exactly the same. Like each letter, each word. And we talked our way out from it.
Do you want a mic to record? No?
Oh, should I? Okay. So this letter was about hidden features, not the obfuscation. There was a recommendation to turn off the obfuscation so they can check our hidden features, but we never did.
Okay, you just uploaded the binary second time, or?
No, we exchanged a lot of emails describing the situation, and yeah, they said, okay, fine, go.
We had the deadline and we couldn't. Yes?
Okay, so it's a cascading question. One of the last slides you compared binary code obfuscation with source code obfuscation. Is it possible to pipe those two kinds of obfuscation? So you source code obfuscate first and then binary, and if so, is it reasonable? Is there any point of doing that?
Yes. A lot of people actually ask me about this, and I think if you try to obfuscate with one and another, it would work, but it's not worth to, because you got only the sum of disadvantages, and all advantages just pass away, so don't try this at home. Yes?
Yeah. So the question is about the signing, because changing the binary, of course, breaks the sign. So you need to resign the binary afterwards, and does the Mach obfuscator do that?
This is MVP, so it does not do yet, but the repo contains a bash script that does it for you. So in the future release, maybe it will do this automatically. Yes?
Does binary obfuscation affect runtime programming, like checking for selectors, going through a list of classes in GTC?
The question is if binary obfuscation affects runtime programming. Yes, it affects the same way that source code obfuscation does. So if you try to retrieve selector by a string, it would break. If you reference selector using add selector, then it would work the same way as source code obfuscation.
So stringly type reflection in GTC would break.
Yeah, exactly. Any more questions? You can chat with me later, or
One more question,
yes?
because you are mentioning that the knowledge about parsing Mach-O files can lead to some other tools. Did you have something particular in mind, like other than obfuscation?
Yeah, you could. I thought about this a while, and I thought about writing some code analysis, some code complexity analysis. My friend thought about security analysis, but nothing particular, just okay. Thank you very much for your attention.